All right, today we are jumping headfirst into the world of ultrasound. We're going to go from the basic physics of how it all works all the way to you, the clinician, dialing in that perfect crystal clear image that makes all the difference. Let's get into it. First things first, we have to get one thing straight right out of the gate. That super expensive, top of the line ultrasound machine, it's only as good as the person holding the probe. Seriously. Unlike a CT or an MRI, ultrasound is all about the operator. The factory presets are just a suggestion, a place to start. It's your skill, your understanding of how to tweak that image in real time that turns a fuzzy, confusing picture into a confident diagnosis. So if you want to be the one driving the exam instead of just watching the screen, we've got to start at the beginning. You have to understand how the image is made before you can really master what you can do to make it better. At its heart, ultrasound is all about something called the pulse-echo principle. And look, it sounds complicated, but it really boils down to three simple ideas. First, the probe sends out a quick pulse of sound and then it just listens for the echo. Second, the machine figures out how deep something is by timing how long it takes that echo to come back. And third, how strong that echo is when it returns determines how bright the dot on your screen is going to be. That's it. And this diagram here, it shows you exactly what's happening. The probe spends only about 1% of its time talking or sending out that pulse, and the other 99% of the time it's listening. An echo that takes longer to get back? Well, that gets placed deeper on the screen. A stronger echo? That makes a brighter pixel. And this happens millions of times a second to build the live image that you see. Kind of wild when you think about it. Okay, so we've got the how. Now let's get our hands on the what. We're going to talk about the main controls you'll be using, but I don't want you to think of them as just knobs and buttons. Think of them as powerful levers that give you total command over the quality of your image. Your very first move, every single time you put a probe on a patient, should be setting the depth. Just look at these three images. If your depth is too shallow, you're literally cutting off anatomy you need to see. But if you go too deep, your area of interest becomes this tiny little thing at the top of the screen, and you're just wasting all that space, which actually hurts your image detail. The sweet spot is having your target take up most of the screen, right in the middle. Next up, we've got gain. Now, you can think of this as the overall brightness control for the entire image. Too low, and everything's dark, and you lose information in the shadows. Too high, and you get that snowy look that just whites everything out. But here's the pro tip: time gain compensation, or TGC. See, sound naturally gets weaker the deeper it goes. TGC lets you individually boost the brightness at different depths, so you get this beautiful, evenly lit image from top to bottom. Now for the big one: frequency. This is the fundamental trade-off in all of ultrasound, and I absolutely love this analogy. High frequency is like your reading glasses. It gives you these incredible, sharp, high-resolution details for things that are right up close to the surface. Low frequency, on the other hand, is like your distance glasses. It can see way deeper into the body, but all those fine details get a little blurry. The key is you can't have both at the same time. So what does that mean for you? It means there's one simple rule you have to burn into your brain. Always use the highest frequency that can still reach your target. Why? Because as you can see here, higher frequency waves are shorter, which gives you better axial resolution. That's just a fancy way of saying it's better at telling two objects apart when one is right behind the other. It's how you get maximum detail where it counts. And our last major lever is the focal zone. You see, the ultrasound beam isn't a perfectly straight line. It's actually shaped like an hourglass. And that narrowest point, the focal zone, is where your image is the sharpest side to side. We call that lateral resolution. Your job here is simple. See that little triangle or arrow on the side of your screen? You need to move it so it's pointing right at or just a little bit below your structure of interest. That's how you get the sharpest image possible. All right, so you've set your depth, dialed in your gain, picked the perfect frequency, and placed your focal zone. You've built the best image you can. But what about when the physics of the ultrasound itself creates things on the screen that aren't actually there? We call those artifacts. And the key thing to realize is that they aren't just mistakes. They're puzzles. And depending on how you read them, they can either fool you or give you some major diagnostic clues. So that brings us to the big question. When you see one of these weird things on the screen that doesn't seem to correspond to actual anatomy, is it a bug in the system that you should try to get rid of? Or is it a feature, a piece of information that the machine is trying to give you? Well, the answer is, it can be both. We can basically split all artifacts into two main groups. On one side, you have pitfalls. These are the tricky ones that can look like real pathology and trip you up if you don't recognize them. And on the other side, you have clues. These are the good ones, the artifacts that are actually super helpful for making a diagnosis. And here are two of the best clue artifacts you'll ever see. On the left, that's acoustic shadowing. See that clean, dark shadow behind the bright white thing? That shadow is screaming at you, hey, I'm super dense. It's what confirms something is a gallstone or a piece of bone. Then on the right, you see the opposite, posterior enhancement. That bright area behind the black circle, that confirms the circle is filled with fluid, like a cyst, because the sound just zipped right through it.
Now for the pitfalls. You've got to watch out for things like this, the mirror image artifact. What's happening here is that the diaphragm is acting like a strong, curved mirror, and it's creating a fake, mirrored image of the liver up in the lung space. It's easy to mistake that for a tumor or pneumonia. Here's the pro move. If you think you're seeing an artifact, just change your angle or move the probe. Real things will stay put. Artifacts will often change or just vanish.
Okay, this one right here might be the most important pitfall, especially if you ever scan muscles or tendons. It's called anisotropy. Look at this. It's the exact same healthy tendon in both pictures. On the left, it's bright and normal. On the right, it looks dark, like it's torn. The only thing that changed was the angle of the probe. It is so important to keep your ultrasound beam at a perfect 90-degree angle to these structures. You have to heel-toe the probe, rocking it back and forth until it's as bright as possible. Phew! We've covered the physics, the machine controls, and the artifacts. So now the moment of truth. Let's put this all together into a simple step-by-step process you can use every single time you scan. Here it is, your diagnostic workflow. Think of it like a pilot's checklist. 1. Start by picking the right probe and the right exam preset. 2. Immediately fix your depth so your target fills the screen. 3. Adjust your overall gain and then fine-tune with TGC for that perfect, even brightness. 4. Move your focal zone to where you need the most detail. 5. Crank up the frequency as high as it'll go while still being able to see your target. And finally, number 6. Now you're ready to actually scan and interpret, keeping an eye out for all those clues and pitfalls. And that brings us right back to where we started with the most important takeaway of all. The presets are just a suggestion. The best image is never made by the machine on its own. It's made by you actively thinking and intelligently optimizing that image for every single patient. That's what makes you a great sonographer. So the next time you pick up that probe, remember, you're in control.